Welcome to the course on design and analysis of algorithms. Our topic today is element distinctness lower bound. This will be a continuation of the previous lecture, which was on sorting lower bounds. Let me start by defining the problem. So the problem is as follows. You are given as input a sequence of numbers. Let me call the entire sequence x, and the individual numbers in the sequence are x1, x2, xn. We are supposed to output a yes answer if all the xi are distinct, and otherwise if some xi equal to xj, some two numbers xi and xj, distinct two numbers xi and xj are identical, then we are supposed to output a no answer. A no answer means that no, all the elements are not distinct. What we are going to prove today is that in the decision tree model, which we talked about last time, and which I will quickly define this time also just for continuity, we will prove that in this decision tree model, the time is going to be n log n. So this is a non-trivial lower bound in the sense that it says that you need to do a little bit more than just examine all the numbers, which would just take omega of n time. It should be quite obvious to you that if you are allowed to use n log n time, then element distinctness can be easily solved. How? Well, in n log n time we can sort all the numbers, and now if two numbers are identical, they are guaranteed to come next to each other. In which case we simply have to compare adjacent numbers after sorting, and that will enable us to find out whether all the numbers are distinct or not. So in summary, in n log n time, we will be able to actually compute whether the numbers are distinct. However, the subject of today's lecture is not that. The subject of today's lecture is to prove that at least n log n time is needed. So we want to prove a lower bound. Here is what I am going to do today. So today I am going to talk about the decision tree model. I am going to go over this rather quickly because it is going to be very similar to what we did last time. Last time we looked at lower bounds on sorting, and we introduced a lower bound technique. So I am going to explain why that lower bounding technique does not work. That seemed like a very nice technique, but it will turn out that that does not really work for the problem which we are looking at today. Then I will talk about a new lower bound technique which works for this problem of element distinctness, and then we will prove the lower bound that I mentioned. Finally, I will extend the model. Okay, so instead of the decision tree model, I will define a more powerful model called the algebraic decision trees model, and I will talk a little bit about it. So let me start with the decision tree model. So in the decision tree model, the input is always going to be a sequence of numbers, say the same sequence x1 through xn, and we will assume that these numbers have already been read into the model. So there are no input instructions as such, the inputs are already read. A program in this model is a labeled tree, and all non-leaf nodes are labeled I:j, where I and j are integers, and these integers have to be fixed as a part of the program. Leaf node, each leaf node has a label which just says what is the value to be output. Okay. Edge labels are relational operators. So less than, equal to, greater than, not equal to, less than or equal to, greater than or equal to. Okay. Let me quickly take an example of a decision tree program. So here is a decision tree program for sorting three numbers. As you can see, each non-leaf node is labeled I:j, in this case 1:2, and each leaf node is labeled by the answer that is to be output, and furthermore each edge is labeled with a relational operator. Execution begins at the root. Okay. At each node labeled I:j, xi from this input set of inputs is compared with xj. Whatever the outcome of that comparison is, the corresponding branch is found with the corresponding label, the corresponding outgoing edge is found, and execution follows that branch, that outgoing edge. So, you go down to the node which is at the other end point of that edge and you repeat this whole thing until you get to a leaf. Okay. When you get to a leaf, its label is output. So, that is the answer that you are going to compute, that you wanted to compute. So, two things to be noted. Okay. So, as we saw in the example, there is going to be a separate program for each input size. So, there is going to be a separate program for n equal to 1, for n equal to 2, for n equal to 3 and so on. And we saw a program for size n equal to 3, not for element distinctness, but for sorting. And then the other point we noted is that although we are looking at a decision tree model, and the decision tree model is not exactly like our computer, like any of our computers, okay, it does in fact have a connection to the RAM model or the random access machine model, which in fact resembles our computers. And this relevance has been discussed in the previous lecture, and let me remind you what that relevance was. So, we said in the previous lecture that if we have a lower bound in the decision tree model, then it applies to the RAM model, not completely, but it applies to comparison based algorithms in the RAM model. Comparison based algorithms are simply algorithms which compare the keys. They do not perform arithmetic on the keys, or they do not use the keys to index into the arrays. They simply compare the keys, and of course, they may copy. So, here is a quick overview of the sorting lower bound. The input to the sorting problem was the sequence x, the same sequence which we have mentioned, consisting of components x1, x2, xn. So, these are all numbers and we want to sort these numbers. The key thing to observe in this problem or in the lower bound argument is that there are n factorial possible answers. So, either I could say that this is the sorted sequence, or I could take a permutation of this and say that that is a sorted sequence. I could take every possible permutation of this and that could be my answer. Every possible permutation could be an answer, and there are n factorial permutations, and therefore, there are n factorial possible answers. This is a very important point in this argument. Now, the answer is going to be printed at a leaf of this tree, of the program tree, which means that if you want to print out n factorial different answers, then you must have n factorial leaves. You have no choice, because a single leaf can just print a single answer. It will print out that entire permutation, but that entire permutation constitutes a single answer. So, if execution arrives to that leaf, then that is the only answer it can print out. So, if your program tree is going to be even capable of printing out n factorial different answers, then it had better have n factorial leaves. But if it does have n factorial leaves, then the height of the tree has to be at least log of n factorial, which is n log n, and in fact, the height of the tree is the worst case time, and therefore, the worst case time taken is at least n log n. So, this is a rough sketch of the argument that we saw last time. This idea that if the answer has n factorial possibilities, or if there are n factorial different answers, in the language of information theory can be expressed as saying that this answer has high information. So, whatever we are going to print out as the answer, if you think of it as a variable, it has a very high information content. The answer can take n factorial different values. So, it has information, the information quantity in it is high, it's as much as something like n factorial. Okay. In fact, information theory measures information as the number of ways, the log of the number of ways. In fact, it is going to be log of n factorial, okay, very roughly. In any case, Bounds of this kind, where we say that there are so many ways in which this variable can take a value, are therefore called information theoretic lower bounds. So, in fact, you will see this sorting lower bound often referred to as the information theoretic lower bound. Let us now turn to the element distinctness problem. How many answers do we have? Well, the answers are only two really. The answer could either be yes, which means all elements are distinct, or the answer could be no. No means some duplicates exist. So, we only have two answers. So, our answer only has two possibilities. Okay. So, log of that is not going to be very large. It is going to be in fact exactly 1. Okay. So, if we just say that there are two possibilities and therefore, there are two leaves, that does not help us much, because log of 2 is 1 and it just says that the tree must have height 1, which is a really silly bound. So, we need to do something better. So, we need to have a new strategy. So, here is a rough sketch of this strategy. So, we will show that there must be at least n factorial leaves. Again, the number n factorial is going to turn out to be somewhat significant, but we will prove that in fact there must be n factorial leaves, all of them giving yes answers. So, this is going to be an interesting argument, and we will be making some rather clever use of n dimensional geometry. Okay. Do not be worried about n dimensional geometry. Most of the time, for the purposes of getting intuition, you can visualize what is going on in 2 or 3 dimensions, and that usually tends to be enough, which is in fact going to be the case in our proof. However, if you want to algebraically write down things, the argument can get a little bit complicated, but fortunately even the algebraic argument that I am going to show you is going to be rather simple. So, here is our main claim again. We are going to prove that the time required for the element distinctness problem is going to be at least n log n on the decision tree model. Let me remind you what this claim means. So, this claim asserts a problem lower bound. It says that the time required for this problem, irrespective of any algorithm, is this. So, it is not a bound on an algorithm. Well, if you want to think about algorithms, it is a bound on all possible algorithms in this model, of course. Here is a quick overview of the proof. The proof is a little bit long, but not terribly so. Okay. The first idea is going to be to interpret our input sequence. Okay, so, we have our input consists of n numbers x1, x2 all the way till xn. So, we are going to think of this n tuple as representing the coordinates of an n dimensional point. So, x1 represents the first coordinate, x2 represents the second coordinate, xn represents the nth coordinate, and the entire thing represents a point, and we will call that point x. We are going to restrict these instances to the unit n cube. What do I mean by that? Well, we are going to insist that all the xi's lie between 0 and 1. We will prove the lower bound under this restriction. So, that should not be a cause of any worry. If we prove the lower bound under this restriction, of course, it works if we do not have this restriction. Okay. So, in fact, if we do not have this restriction, who knows, things can get even much worse, but we are not worried about that. We just want to argue that things can certainly get at least as bad as this. Okay. And so, it is okay to have this restriction. Here is the first claim that we are going to make. We will use the notation R of L, which stands for the region of L. Okay. So, the region of L, where L is a leaf, is the set of all input instances for which leaf L is reached on execution at the end of the execution. Okay, so, this is the definition of what R of L means. what we are asserting is that this R of L is connected. I will explain to you what connected means in just a minute, okay. But it is the usual notion. Okay. So a region is connected if it looks together, okay, or if there are 2 points in it and they can be joined by a path within that region. We will do this a little bit more formally and we will write it down in a minute. The second claim goes something like this. Suppose we have a point x whose coordinates are distinct. Okay, so this sequence consists of distinct elements, or alternately these coordinates are distinct. Now we take y, which is a non-trivial permutation of these coordinates. So we rearrange these coordinates, we reorder them such that this sequence and this sequence look different. That is what x and y are. So the main claim is, and this is the key claim in this entire proof, x and y must reach distinct yes leaves. So the point is this, that this will allow us to argue that there will at least be 2 distinct leaves, or who knows more. And then we will argue, in fact, based on this essentially, that the number of yes leaves is bigger than n factorial. The time is simply going to be the height of such a tree, okay, and it is going to be log of n factorial or n log n. So this will immediately follow from this. We will see that later. So let me go over each of these items and let me explain each of these items. So let us start with this. We are going to interpret this x as a point in n-dimensional space, and of course we are restricting the points to the unit in cube. As I said, it is hard to visualize n-dimensional space, so we are just going to live with 2. We will visualize 2-dimensional space and we will see what happens. And you will note that even if we work with 2 dimensions, we will get enough of the insight. So here is our visualization. So our instance is this x with first coordinate x1, second coordinate x2. So this is our x1 axis, this is our x2 axis. Our instance has come from the unit cube. So here is the unit cube in 2 dimensions. This entire interior is the unit cube. So this is 1, this is 1. Okay, so this is where our instance has come from. What I mean by that is I pick a point over here. Its first coordinate is the x1 value, its second coordinate is the y1 value. So let me continue the analogy a little bit further to show you what, to make sure that we understand at least this case of 2 dimensions very well. I claim that all the instances which lie on this diagonal are no instances for this problem of size 2. Well, what are the instances which lie on this diagonal? So the instances on the diagonal simply are those points whose x1 coordinate is exactly equal to the x2 coordinate. But if the x1 coordinate is equal to the x2 coordinate, then we know that the elements are not distinct, and therefore these points on the diagonal are in fact the no instances. The interior of this triangle and the interior of this triangle are the yes instances. Why? Because if I pick a point in it, I know that the x and y coordinates cannot be equal. The x and y, well, the x1 and x2 coordinates cannot be equal. Similarly over here, this is the line which divides the square into 2 parts, and this is the line on which the x1 and x2 coordinates are in fact equal. So what we have done over here is we have taken our problem and we are viewing it geometrically, and you will see that this geometric viewpoint gives us some interesting insights. Okay, so we have finished interpreting this the instances in a 2-dimensional space, or in particular in an n-dimensional space. Okay, so we have finished this part. We interpreted our input instance as a point in n-dimensional space. Well, in this case it was just 2-dimensional space, but you should get the idea. and we also restricted the instance to the unit n cube, which in this case was just the unit square. Now we want to prove this claim. Okay. So this and this are the two main claims. This claim says that if we look at the region of this cube, from which instances will reach L, then this region is going to be a connected region. So let me start by defining what connected means. A connected region in n-dimensional space, so is as follows. A region R is said to be connected if for any points x or y in R, there exists a path from x to y passing entirely through R. So we have any points x and y in R, and there exists a path from x to y which goes only through the points in R. So what is a connected region? So the cube that we mentioned, for example, is a connected region, the interior of it. Well, the surface of it is also a connected region, certainly. Let me now define a convex region. So this is going to be needed in the proof. A region R is said to be convex if for any points x and y in that region, the straight line path from x to y passes entirely through R. So here we just said that any path, that some path passing through passing from x to y must pass entirely through R. Now we are making a stronger requirement. So we are now saying that in particular the straight line path from x to y must pass through R. Notice that convexity is only a special case of connectivity. So in other words, if we know that a certain region is convex, then it has to be connected, of course. So the reason why we worry about convexity is that if we look at only straight line paths, they are very easy to reason with, and therefore it is often much easier to argue that a certain region is convex. So convexity of a region is easier to prove, and therefore we are worried about convex regions. But notice that if we prove that something is convex, we are also proving that it is connected. So some examples. Examples of convex objects are the cube, the whole cube or the whole sphere. Examples of objects which are connected but not convex, say something like a torus. So let me draw out a picture. So if we have a torus, so it has a hole in it. So if I pick a point x over here and a point y over here, then the line joining them, the straight line joining them would pass through this region, which is not in R. So this torus itself is in R, but this region is not in R. A kidney shaped region or a cashew shaped region is also not convex, because I can pick a point x over here, a point y over here, and this line passes outside the region. If I look at a cube, and if I just look at its surface, not the interior, but if I just look at its surface, then if I pick a point over here and a point over here on this face, then the line joining them the straight line joining them will pass through the interior, which is not in this region R, and therefore this shell is not convex either. Okay, so that describes what connected means formally and also what convex means. So here is our claim. So we claim that R of L is the set of instances for which leaf L is reached on execution, and then we want to argue that R of L is convex. Well, actually we wanted to argue that it is connected, but we will in fact argue that R of L is convex, which will assure us that it is also connected. Let me pictorially remind you what this R of L is. So here is our decision tree, and this is a leaf L. So what is this region that I am talking about? Well, if I start with any instance x and suppose I follow this path and I reach L, then I will say that this instance belongs to R. If execution arrives at L. Okay, so then it belongs to R of L, the region of L. So let me first begin by giving some intuition. So I said that X is the set of points such that if I start from here and eventually I get to L. So what do I know about X? Well, each node that is visited has some condition associated with it. So maybe here the comparison is between I and j, and say this is the less than path. Then these two together say that this x must satisfy xi less than xj. Maybe this label over here is kl, and say this is the equal to path. Then this says that the condition satisfied must be xk equal to xl. So if any instance gets to this label L, I know that all of these conditions along this path must be satisfied. So this is one way to characterize the region, the set of points which reach L during execution. But notice that this characterization is geometric. So this just says that the ith coordinate is smaller than the jth coordinate. So this is naturally putting our region R of L into some parts in our unit cube. So let us start with this root itself. So which are the instances which can visit the root? Well, at the root, any instance will arrive. Okay, so in fact, any x in the entire unit cube will arrive at the root, will start at the root. So instances visiting the root constitute the entire cube. What about instances visiting this node? So this node is visited by those instances for which xi is less than xj. Now here is the key insight. So asserting that xi is less than xj is equivalent to saying that if this is our unit cube, okay, now I am looking at 3 dimensions, and maybe this is some x1, this is x2, and this is x3, and if I say that x3 is say less than x1, what do I do? Well, I will look at this x3, okay, and I look at this x1, and then I look at first that portion where x3 is equal to x1. So it is this plane. Let me just shade it. Okay. So it is this slice through the center of that cube. That is where x3 is equal to x1. And if I want x3 to be smaller, then which side should I take? Then x1. So I want x1 to be larger and x3 to be smaller. So in fact, this is this entire region. Okay. So in fact, it is this region, the wedge-shaped region that is facing us. Okay. So the idea is this: the moment I assert a condition, I am going to slice my current set, and I am going to take one part of it. If my assertion was something like x3 equal to x1, then I won't take one part, but I will take that slicing region itself. So notice that I started off with the entire cube which is convex, and the important point is that whenever I go to a child as in this, I am going to shrink the set of instances which visit this, and when I shrink them, I will be shrinking them in a convex manner. So I will sort of take my region, okay, I will take a region which is convex, then I will slice off a part of it. But this slicing operation maintains convexity. So that is roughly the idea. So even if I do it several times, the region that I am left at with the at the end is going to be a convex region and therefore also a connected region. That is roughly the argument. So, now we are going to see it more formally. So, here is the proof. Suppose x and y are 2 points in R in this region. So, I am going to consider 3 executions. In the first execution, the instance is going to be x. Okay. What do I know about this? I know that L is reached, okay, by definition, by our assumption that x and y are points in R of L. So, when I finish this execution, I know that L is reached. In execution 2, I am going to start with y. What do I know about this? Well, I know that for this point as well, L is reached. So, even for this point, L is reached, right. Again, that is because I said that y belongs to R of L, which is nothing but saying that if I do an execution with my instance equal to y, I will reach that same leaf. My third execution is the interesting execution. Here, I am going to start off with an instance which I will call z. Z, let me remind you, has n coordinates just like x and y. So, I will call those z1, z2 all the way till zn. And I am going to set zi in a curious looking manner. Zi is going to be lambda times xi, where lambda is some positive number between 0 and 1. I will tell you more, I will write that down in a minute. And lambda times xi plus 1 minus lambda times yi. So, this is how each zi is going to be set. So, it will be some kind of an average of xi and yi, okay, where the weights for xi are lambda and the remaining weight comes from y. So, if I take the case lambda equal to 0, what does it mean? So, if I take lambda equal to 0, then this part goes away and I get y. If I take lambda equal to 1, this part goes away and I get x. And if lambda is somewhere in between, what do I get? If lambda is equal to half, then I get half of this and half of this. And in fact, I get the midpoint of the line segment xy. If I take other values of lambda, I will likewise get points on the line segment joining x and y, the straight line segment joining x and y. So, this is the key behind, this is the key part of the definition of z. I am going to, I have defined z so that it happens to be on this straight line xy. Okay. And so long as I restrict lambda between 0 and 1, it will be in the interior of this line segment xy. So, what do I have to prove in order to argue that this R of L is convex? Well, the definition says that the straight line path must lie inside R of L. If I prove that, then I am done. So, that is exactly what I am going to do. So, I am going to analyze this execution 3 and figure out what happens during execution. So, let us start with the root. The root label is I colon j, and suppose the less than branch is taken in execution 1. I am just taking this as an example. The argument will really work for every possible branch. So, the less than branch is taken in this execution. Okay. In this execution, what do I know about this execution? Well, clearly the same branch will be taken in execution 2. Why? Well, in execution 2 we reach finally the same leaf, and there is only one way to get at that leaf, and therefore it had better be along the same path. So, even in this second execution we are going to follow the same branch. What can we conclude from that? So, from the fact that in the first execution this branch was taken, it clearly means that xi and xj got compared and xi turned out to be less than xj. In the second execution, yi and yj got compared and yi turned out to be less than yj. So, this is what we know if we assume that the less than branch was taken in this execution. Now, I am going to multiply this by lambda and this by 1 minus lambda, and I am going to add these two things. So, let us see what happens. So, I claim that I get this inequality. Let us check that out. So, on the left hand side, I am going to get from this inequality lambda times xi, which I have got over here. From this, I will get 1 minus lambda times yi. This is what I have got over here. On the right side, I got lambda times xj from this inequality, and from this inequality, I got 1 minus lambda times yj. So, what we have now is this inequality. So, this is the inequality that we got. Let me just complete this argument. Okay. So, to complete this argument, what we have is that this part is simply Zi and this part is simply Zj. So, this is Zi, this is Zj. So, we have concluded that Zi must be less than Zj. But that is what we wanted. Why? Because if Zi is less than Zj, we know that the less than branch will also be taken in execution 3. So, for this first root, we have proved that execution 3 will follow the same path as that followed by execution 1 and execution 2. So, this argument can be made if instead of less than we took some of the other and we can make it at every node along that path, and so we can argue that finally L is going to be reached. So, what we have argued is that Z will reach L, Z is any point on this line segment, and so if I start with any point on this line segment, I reach L, and therefore, I have concluded that R of L is convex. So, I have proved this claim. So, let us now turn to the next claim. So, this claim says that if I have a point or an instance x whose all coordinates are distinct and y is another is a permutation of this which is not exactly equal, then x and y must reach distinct leaves. Of course, they must reach yes leaves because their coordinates are all different, but in fact, the claim asserts that they must reach distinct yes leaves. So, we are going to prove this. Okay. So, x consists of distinct values means the answer of x must be yes. Y is some permutation sigma. Okay. So, the answer to y is also a yes. We are going to prove this result by contradiction. Okay. So, we are going to assume that say x and y reach the same leaf L. Then we know that the region corresponding to every leaf L is a connected region. Okay. If it is a connected region, then there has to exist a path P from x to y which passes entirely through L. This is what we know from the previous claim. So, what we will show that if you tell me that it is this path, I will show that there exists a point Z on this path P such that the answer to Z is a no. Now, this will be a contradiction because Z lies on P is supposed to lie inside R of L, okay. And what we have argued is that the answer is no, whereas the answer for L is supposed to be yes. So, this would be the contradiction. So, this is what we are going to do. Let me start with a subclaim. The subclaim says that there have to exist I and j such that the ith coordinate of x is strictly less than the jth coordinate of x, whereas the ith coordinate of y is bigger than the jth coordinate of y. I will prove this in a minute. but let me just examine its implications. So, in fact, this is going to give us the proof almost immediately. So, let me define a function f in this space, where f for a point w is simply the difference between the ith and the jth coordinates. So, what is f of x? F of x is xi minus xj, but xi is smaller than xj, so f of x is less than 0. What is f of y? Well, yi is bigger than yj, so yi minus yj is bigger than 0 and fy is bigger than 0. So, f of x is less than 0, f of y is bigger than 0, they are joined by this continuous path p. So, what happens as we move along this path from x to y? The path is continuous, this is a continuous function, and so by the mean value theorem there has to exist a point z on p such that f of z is equal to 0. If f of z is equal to 0, what does it mean? This means that zi equal to zj, but if zi equal to zj, then the two coordinates are equal, that means the answer to this z is no. The coordinates are not distinct, so the answer is a no. But this was supposed to be a point inside R of L, okay, so the answer had better have been yes, so there is a contradiction. So, we have proved our basic claim. So, all that remains now is to prove this subclaim. So, let us prove that. So, the claim is that there exists ij such that xi is less than xj and yi is less than yj. So, I am going to do this with an example to help you understand what is going on. So, here is my example. So, I am looking at say a 5-dimensional space, this is my x, the coordinates are all points in the unit cube. Okay. This is y, remember that y is just a permutation of this permutation sigma. Okay. And y is such that it is not identical. So, the same numbers as x are repeated over here, but it is not repeated, they are not repeated identically. Well, they can be identical at one place, that is okay. Now, here is the key step. I am going to define a permutation pi which sorts x. Okay. So, pi of x then is going to simply take these and rearrange them in increasing order. So, it is going to be 0.2, 0.5, 0.7 and so on. It may not be clear to you why I am defining this permutation pi, but please bear with me. The answer will hit you in a minute. So, I know what this pi is, I know how to take x and generate pi from it, pi of x from it. I apply this same permutation on y as well. So, what happens? Well, I look at the same the column of x which moved over here, and I take the corresponding value for y and move it down over here. So, it's both are 0.2 over here, so both are 0.2 over here. Then 0.5 came from here, so the value over here must also come over here. 0.7 came from here, so below it is 0.9, so over here also below it there is 0.9. Then we have 0.8, 0.7 from this and 0.9, 0.5 from here. Okay, so we have rearranged x and we have rearranged y. Now, be patient with me just for a minute. I am going to prove this claim, but I am going to prove it for pi x and pi y, where it is very easy to see, and you will see that I can just trace it backwards to x and y. So, what does it mean to prove the claim for pi x and pi y? Okay. Well, we are supposed to find ij of this property. Okay, so, because we sorted, and here is now the reason for sorting it, if I is less than j, we know that pi of xi has to be less than pi of xj, right, because this is sorted order. So, pi of xi, x sub I, the ith component of pi of x must be smaller than the jth component of pi of x. So, this is smaller than this is smaller than this and so on. So, so long as I choose I smaller than j, this first property is guaranteed to me. What do I know about y? So, here is one sequence, I change that and I permute it. So, I know now that somewhere this new sequence has to be non-increasing. This was an increasing sequence, this is a permutation of it. So, somewhere this sequence has to be non-increasing. So, let us say that there exists ij such that I less than j, and If it is non-increasing, then that means pi yi must be greater than pi yj. But notice then we have found these two. Okay. So, we have found ij such that pi yi is bigger than pi yj, whereas pi xi is bigger than pi xj. So, just to illustrate in this example, here is the case where this is smaller than this, but this is larger than this. Now, we have proved it for this pi x and pi y. How do we go back? Well, the idea is simply we figure out where these columns came from our original example. This column came from here and this column came from here. And sure enough, this number is less than this, whereas this number is greater than this. Okay. So, I will skip the algebra, but this is exactly what is happening. We just have to follow it back and then this property will hold nevertheless. So, what have we proved? Well, we have proved this claim, and this was all that was needed to prove our original claim, which was this. So, once we prove this claim, what do we know? That if we have two distinct permutations of this, if we have a distinct permutation of this, then that must reach a different region. But now I know that the number of distinct permutations can be n factorial, and therefore, the number of S leaves has to be bigger than n factorial, and the time has to be bigger than the height of that tree, which is height log of n factorial, or at least n log n. So, this finishes the claim that the time for element distinctness is at least n log n on decision trees. Here is a quick summary of the argument. So, what we did here was that we said that the instances visiting any S leaf form a connected region in the instance space. No instances partition the instance space such that distinct permutations are not in the same connected region. And therefore, we concluded that the number of S leaves must be large. What is the implication for the RAM model? Well, for the RAM model, we can conclude exactly using ideas similar to last time, that the comparison based algorithms for element distinctness must take time n log n. I want to quickly extend this to the case of algebraic decision trees. So, here is a quick definition. So, again, the program in this model consists of trees with outgoing branches less than, equal to, or greater than. But this time we will just have these three relational operators just for simplicity, although you can have other operators too. The node labels are no longer I colon j, but they are algebraic expressions, okay, over the input, the components of the input. So, x1 squared plus x2 squared minus 25. The action is we are going to evaluate the label expression and we are going to compare it to 0. So, if this expression is equal to 0, then we will choose the equal to branch. If this is less than 0, then we will choose the less than branch. So, let me just take a quick example. So, if our expression is x1 squared plus x2 squared is minus 25, then the condition x1 squared plus x2 squared minus 25 is less than 0 simply means that our point lies inside this. Okay. So, we are restricting our point to be inside this region. If the expression is linear instead of this, which is a quadratic, then our previous results actually hold. Unfortunately, if the expression is non-linear, okay, then the intersection of constraints can produce disconnected regions, which cannot happen if things are linear. The main result is something like this. This is a deep result actually from algebraic geometry. So, we have a decision problem over inputs x1 to xn. By a decision problem, we simply mean a problem whose answer is yes or no, just like element distinctness. Suppose A is an algebraic decision tree algorithm for the problem such that the degree of each algebraic expression is some fixed constant d. So, x1 squared plus x2 squared would be degree 2. Suppose the no answers partition the instance space W into W connected regions, within each of which the answer is yes. So, in our case, for for simple decision trees, this W for the element distinctness was n log n. But in general, the time required is going to be, by this algorithm, is going to be omega of log of W minus n. Now you might wonder what happened to that D. So this D actually appears inside this omega. So there is a constant of proportionality which depends upon D. For decision trees, the time is log of W, not even omega, it's actually just log of W, and log of W to base 2. Okay. So what this theorem says that the complicated algebraic model doesn't really help all that much. Okay. So the lower bound that we get is almost as good. Well, it's a little bit smaller because of this minus n, and maybe the proportionality constant is a little bit different, but it's essentially the same lower bound. For element distinctness, in fact, there is no change. The algebraic tree for any fixed degree will give us n log n as before. The proof idea is actually pretty difficult. Now, as we said, a single leaf can correspond to a small number of connected regions, not just exactly one connected region. So now we have to get some heavy duty machinery from algebraic geometry to count the number of connected regions that you get when you take intersection of several constraints. If the constraints are linear, then it's very simple. If the constraints are high degree algebraic expressions, then this becomes rather complicated. So quickly summarize. Lower bound theory that we have been looking at in the last 2 lectures tells us when to stop searching for better algorithms. This is very good because it's good to know that you are done. Another interesting point of this theory is that it has connections with some really deep mathematics. Algebraic geometry is supposed to be a rather deep area of mathematics, and it has connections to many other fields also. Here is a very simple context in which this idea can be used. So I'll leave it as a problem for you. Suppose you have 27 coins such that 26 have equal weight and one is heavier. Find the heavier using 3 weighings. This is probably a puzzle that you have solved. Okay. Now I want you to use the ideas expressed in this lecture to formulate a decision tree like model using which you should be able to argue that you cannot do this in fewer than 3 weighings. Thank you.